Whenever the day comes to a close and the noise of the world finally begins to quiet down, there is a subtle shift in the way we perceive our surroundings. The bright, demanding light of the sun slips beneath the horizon, painting the sky in fading shades of twilight. As the atmosphere cools and the shadows lengthen, a deep and comforting darkness takes over, and in that darkness, a magnificent canvas reveals itself. We look up, and we see the stars. For as long as humanity has possessed the capacity to wonder, we have tilted our heads upward and stared into the infinite quiet of the night sky. We have connected the dots of starlight to tell stories, we have used them to navigate across vast and uncharted oceans, and we have wished upon them in our quietest moments. But beyond the stories and the navigation, there has always been a deeper, more profound question echoing in the silent spaces between the stars. It is a question born of both curiosity and a strange, quiet longing. We wonder if we are alone. We wonder if, somewhere out there in the unfathomable depths of the cosmos, there is another place like ours. We are searching for an echo. We are searching for the closest thing to Earth, 2-0. To understand the magnitude of this search, we must first take a moment to appreciate the fragile beauty of the world we currently inhabit. Earth is not merely a sphere of rock drifting through the vacuum of space. It is a masterpiece of delicate balances. It is a world where the temperature is just right for liquid water to pool into vast, deep oceans, to flow in winding rivers, and to fall from the sky as gentle rain. It is a world wrapped in a thin, protective blanket of atmosphere, shielding us from the harsh radiation of the sun while holding in the warmth we need to survive. It is a world of whispering forests, silent deserts, and ice-capped mountains that touch the clouds. Every breath of wind, every drop of dew, every rustling leaf is a testament to the miraculous improbability of our existence. For a long time, we believed that this delicate combination of circumstances might be a solitary accident, a beautiful anomaly in a cold and indifferent universe. But as our vision has expanded, as our instruments have grown more patient and more precise, the universe has begun to whisper a different story. The concept of Earth, 2-0, is not about finding an exact identical replica of our world. It is not about finding continents shaped like ours or oceans filled with the same currents. The universe is infinitely creative, and it rarely repeats itself in exact detail. Instead, the search for Earth 2W0 is about finding the same potential. It is about locating a world that possesses the fundamental ingredients and the serene stability necessary to cradle life as we understand it. We are looking for a sanctuary in the dark. We are looking for a planet of the right size, composed of the right materials, orbiting the right kind of star at precisely the right distance. Imagine, for a moment, the sheer scale of the cosmos. Our galaxy alone, the Milky Way, is a sprawling, spiraling city of stars. It stretches across distances so vast that light itself, traveling at unimaginable speeds, takes 100,000 years to cross from one edge to the other. Within this galactic city, there are hundreds of billions of stars. For generations, we could only look at those stars and guess if they had planets of their own. The glare of a star is so overwhelmingly bright that any small, rocky planet orbiting it is completely lost in the light. Trying to see a planet from across the galaxy is like trying to spot a single firefly hovering next to a searchlight from thousands of miles away. It requires acquired patience and a brilliant shift in perspective. Astronomers realized that they did not necessarily need to see the planets directly to know they were there. Instead, they simply needed to watch the stars and wait. They built instruments of incredible precision, space telescopes designed to float in the silent cold above our atmosphere, free from the blurring effects of Earth's air. These telescopes were not built to take magnificent, colorful pictures. They were built to stare. They were designed to fix their unblinking mechanical eyes on thousands of stars at once, watching for the slightest, most subtle changes in their brightness. This technique, known as the transit method, is a beautiful exercise in cosmic observation. When a planet orbits a star and its path happens to align perfectly with our line of sight, The planet will occasionally pass in front of the star. As it does, it blocks a tiny fraction of the star's light. The change in brightness is minuscule. It is a dip of perhaps a fraction of a percent, lasting for only a few hours. To the human eye, it would be completely imperceptible. But to the patient sensors of a space telescope, it is a clear and undeniable signal. It is a shadow falling across the face of a distant sun. When astronomers see this rhythmic repeating dip in starlight, they know they have found a planet. By measuring exactly how much light is blocked, they can determine the physical size of the world. A larger planet will cast a larger shadow, blocking more light. A smaller planet, a rocky world closer in size to our own Earth, will cast only the faintest whisper of a shadow. And by measuring the time between these transits, the length of the planet's year, they can calculate exactly how far the planet sits from its host star. Through this quiet, patient observation, a revolution has taken place in our understanding of the universe. Just a few decades ago, the only planets we knew of were the ones sharing our own solar system. Today, we know of thousands of worlds orbiting distant stars. We call them exoplanets. The night sky is no longer just a canopy of lonely stars. It is a crowded, bustling landscape of unseen worlds. They are out there in the dark, spinning and orbiting, bathed in the light of alien suns. There are gas giants larger than Jupiter, orbiting so close to their stars that their atmospheres are boiling away into space. There are solitary rogue planets cast out from their home systems, drifting alone through the freezing void of interstellar space. There are worlds entirely covered in deep, planet-wide oceans, and worlds where it rains glass sideways in howling winds. But among this diverse and wildly varied collection of celestial bodies, the telescopes keep looking for something specific. They are sifting through the data, watching the shadows, hoping to find a whisper that matches the dimensions of our own home. They are looking for a quiet, rocky sphere, not too big, lest it hold on to a crushing atmosphere of thick gas, not too small, lest its gravity be too weak to hold on to any atmosphere at all. It must be a world with enough solid ground to stand on, a world that could support the weight of an ocean. When a candidate is found, when the data reveals a planet of roughly Earth's size, a quiet thrill ripples through the scientific community. But size alone is not enough to make an Earth 2. Oh, a rocky planet can be a dead, scorched wasteland if it sits too close to its star. It can be a frozen, silent tomb if it drifts too far away. The physical dimensions of the planet are only the first piece of a much larger, much more delicate puzzle. To find a true reflection of our world, we must look not just at the planet itself, but at the empty space it travels through. We must look at its orbit. We must follow it into the gentle, balancing act of the habitable zone. As we leave the initial discovery behind, we drift further into the mechanics of what makes a world a potential home. We move from the simple geometry of shadows into the complex, beautiful relationship between a planet and the star that gives it light. To find the closest thing to Earth, 2-0, we must search for harmony. A planet is entirely at the mercy of its host star. The star dictates the climate, the seasons, and the very possibility of anything complex existing on the planet's surface. In the vast, freezing emptiness of space, a star is a campfire, offering warmth and energy to the bodies that circle it. But just like a campfire, proximity is everything. If you stand too close, the heat is unbearable, searing and destructive. If you stand too far away, the warmth cannot reach you, and you are left in the bitter cold of the night. In astrophysics, this delicate region around a star, where the temperature is just right, is known as the habitable zone. It is also affectionately called the Goldilocks zone, a nod to the old story of finding the bowl of porridge that is neither too hot nor too cold, but just right. It is a poetic name for a profound scientific concept. But what, exactly, defines this just right temperature? The answer lies in a substance that is utterly essential to life as we know it, liquid water. Water is a miracle of chemistry. It is a universal solvent, a medium in which complex molecules can interact, combine, and evolve. Without liquid water, the biological processes that define life on Earth would grind to a halt. It is the lifeblood of our planet. Therefore, when astronomers search for a second Earth, they are searching for a world where water could exist in its liquid state on the surface. If a planet orbits closer to its star than the inner edge of the habitable zone, the stellar radiation is too intense. Any water on the surface would heat up and turn into vapor. This water vapor would fill the atmosphere, trapping even more heat in a runaway greenhouse effect, much like what we see on our neighboring planet, Venus. The oceans would boil away into space, leaving behind a dry, baked landscape of cracking rock under a thick, suffocating sky. It is a harsh and silent environment, devoid of the gentle flow of rivers or the cooling touch of rain. Conversely, if a planet orbits beyond the outer edge of the habitable zone, the star's warmth is too weak to sustain liquid water. The surface temperatures plunge far below freezing. Any water on the planet would lock up into solid ice. The oceans would be frozen solid, perhaps miles deep, covering the world in a brilliant reflective shell of white. While life might potentially survive deep underground or in subsurface oceans heated by internal friction, the surface itself would remain a silent, frozen desert locked in an eternal winter. The habitable zone is the narrow, quiet corridor between these two extremes. It is the orbital band where a planet receives just enough energy from its star to keep water flowing, but not so much that it boils away. It is a region of gentle warmth, a place where clouds can form, rain can fall, and oceans can lap against rocky shores. However, the habitable zone is not a fixed distance in space. It is not a universal measurement that applies to every star system. The location and the width of this life-sustaining corridor depend entirely on the nature of the star itself. And stars, like planets, come in a wide variety of sizes, temperatures, and colors. Our Sun is a yellow dwarf star. It is a relatively calm, stable, and moderately bright star. In our solar system, the habitable zone extends roughly from just beyond the orbit of Venus to just past the orbit of Mars, with Earth sitting comfortably in the middle. Our world has been traveling within this temperate band for billions of years, bathed in the steady golden light of our Sun. But the universe is mostly filled with a different kind of star. When we look out into the Milky Way, the vast majority of stars are much smaller, much cooler, and much dimmer than our Sun. These are the red dwarfs. They are quiet, long-lived embers, burning through their nuclear fuel at an incredibly slow pace. Because they emit far less heat and light, their habitable zones are pulled in much closer. If we are to find the closest thing to Earth, there is a very good chance it will be found orbiting one of these red dwarf stars, simply because there are so many of them. Imagine standing on the surface of a rocky planet in the habitable zone of a red dwarf. The sun in the sky would not be a brilliant, blinding yellow. Instead, it would be a large, deeply crimson orb, hanging heavy and low. The light washing over the landscape would be a soft, eternal sunset, painting the rocks and any potential oceans in shades of deep red and dark orange. It would be a profoundly different aesthetic from our bright blue days, yet technically the temperatures could be identical to a spring afternoon on Earth. But orbiting so close to a star brings its own unique set of circumstances. When a planet is pulled close to its host star, the gravitational forces become immense. Over time, the planet's rotation begins to slow down, caught in the gravitational grip of the star. Eventually, the rotation locks into place. This phenomenon is known as tidal locking. It is the same process that keeps one face of our moon constantly pointed toward Earth. If our candidate for Earth 2.0 orbits close enough to a red dwarf to be in the habitable zone, it is highly likely to be tidally locked. This means the planet does not experience days and nights. One half of the world is permanently locked in the warm red daylight, forever facing the star. The other half is plunged into eternal darkness, facing out toward the cold, star-studded void of deep space. At first glance, a tidally locked world might seem completely inhospitable. The day side could be a scorching, arid desert under the relentless glare of a never-setting sun. The night side could be a freezing, icy wasteland where temperatures drop close to absolute zero. But the universe has a way of balancing extremes. The key to this balance is the planet's atmosphere. If this Earth-sized world has a thick, dynamic atmosphere, something incredible can happen. The heat building up on the day side can be transported by powerful global winds across the twilight boundary and into the night side. These massive air currents would act as a planetary air conditioning system, distributing the warmth and preventing either side from reaching complete extremes. In this scenario, the most habitable part of the planet, the truest reflection of an earthly environment, might not be directly under the sun, nor in the deepest dark. It would be found in the Terminator line, the permanent band of twilight that rings the globe, separating day from night. In this eternal dusk, the temperatures could be perfectly moderate. Glaciers from the dark side might melt as they cross into the light, forming rivers that flow into temperate oceans before evaporating under the eternal sun. Finding an Earth-sized planet in the habitable zone is a monumental achievement. It requires sifting through mountains of data, waiting patiently for the subtle dimming of a star, and carefully calculating orbits. But even when we find a rocky world sitting at exactly the right distance from its star, bathed in exactly the right amount of light, the mystery is far from solved. A rock in the right place is just a rock. To truly be considered an Earth 2.0, a planet needs more than just a favorable orbit. It needs a shield, it needs a breath, it needs an atmosphere. As we continue our journey deeper into the cosmos, we must look beyond the solid surface of these distant worlds. We must look at the invisible layers of gas that surround them. We must look for the chemical signatures of life, the delicate breath of a living planet slowly writing its story in the starlight. When we gaze into the quiet depths of the night sky, we are looking at a universe filled with potential. We have learned how to find rocky worlds, and we have learned how to measure their distance from the warming fires of their stars. We have identified the habitable zones, the gentle corridors where water might pool and flow. But a planet is more than just a sphere of rock in a favorable orbit. To be a true candidate for Earth 2.0, to be a place where life might take root and flourish, a world must possess a fragile, invisible layer of protection. It must have an atmosphere. An atmosphere is a planetary breath. It is a complex mixture of gases that clings to the surface of a world, held close by the invisible hand of gravity. On Earth, our atmosphere is a delicate balance of nitrogen, oxygen, argon, and a symphony of trace gases. It is what gives the sky its deep, calming blue during the day, and it is what scatters the light of the setting sun into brilliant shades of orange and red. But an atmosphere is far more than a beautiful optical illusion. It is a vital shield against the immense, silent dangers of space. Space is an unforgiving environment. It is flooded with energetic particles, ultraviolet radiation, and the debris of cosmic collisions. Without an atmosphere, the surface of a planet is exposed to the full, unmitigated fury of its star. The intense radiation would shatter the complex molecules necessary for life, sterilizing the ground and evaporating any liquid water into the void. This is the fate of worlds without a sufficient blanket of air. Mars, for example, once had a thicker atmosphere and flowing rivers. But over billions of years, its atmosphere was stripped away by the solar wind, leaving behind a cold, dry, red desert. To find Earth 2.0, we must find a world that has held on to its air. This is a delicate and complex requirement. The ability of a planet to retain an atmosphere depends on a delicate interplay between the planet's gravity, its magnetic field, and the behavior of its host star. A small, rocky planet must have enough mass to pull the gases close. But even a massive planet can lose its atmosphere if it lacks a magnetic field to deflect the solar wind, the continuous stream of charged particles pouring outward from the star. Our Earth is protected by a powerful magnetic field generated by the churning molten iron in its deep interior. This invisible force field surrounds our planet, deflecting the solar wind and preventing it from stripping away our atmosphere. When we look for an Earth 2.0, we are quietly hoping to find a world with a similarly protective shield. We are hoping to find a planet with a warm, active core, generating a magnetic field strong enough to preserve its delicate envelope of gas. But even if a planet possesses a thick atmosphere and a strong magnetic field, we must still ask a crucial question: what is that atmosphere made of? The composition of the air is just as important as its presence. An atmosphere composed entirely of heavy, suffocating gases like carbon dioxide, such as the one shrouding Venus, would create a runaway greenhouse effect, transforming the planet into a searing, inhospitable inferno. An atmosphere dominated by light gases like hydrogen and helium, like those of Jupiter and Saturn, would result in immense pressures and violent, swirling storms, fundamentally unlike the calm, breathable air of Earth. To determine the composition of an exoplanet's atmosphere, astronomers employ a beautiful and subtle technique called transit spectroscopy. As we discussed earlier, when a planet passes in front of its star, it blocks a tiny fraction of the star's light. But if the planet has an atmosphere, something remarkable happens. A small portion of the starlight passes through the planet's atmosphere before reaching our telescopes. As the light travels through the alien air, the gases in the atmosphere absorb specific wavelengths or colors of that light. Every chemical element and compound has a unique signature, a specific pattern of light that it absorbs. By carefully analyzing the starlight that has filtered through the planet's atmosphere, astronomers can read these signatures. They can look for the fingerprints of different gases, deciphering the chemical makeup of an alien sky from trillions of miles away. This is an incredibly difficult and delicate process. The layer of atmosphere around a rocky planet is incredibly thin compared to the vast size of the star. The starlight that filters through it is incredibly faint. But with the advent of powerful new space telescopes, equipped with massive mirrors and highly sensitive instruments, we are beginning to peel back the layers of these distant worlds. We are beginning to see the chemical composition of their skies. When astronomers look at the atmospheres of potential Earth 2 W0 candidates, they are searching for specific combinations of gases. They are looking for biosignatures, chemical imbalances in the atmosphere that might indicate the presence of life. On Earth, our atmosphere is rich in oxygen and methane. These two gases react readily with each other, and under normal circumstances, they should not coexist in large quantities. The only reason our atmosphere contains so much oxygen and methane is because they are constantly being replenished by biological processes, by plants producing oxygen through photosynthesis, and by microbes producing methane as a byproduct of digestion. If astronomers were to find a rocky planet in the habitable zone, and if they were to detect a strong signature of both oxygen and methane in its atmosphere, it would be a profound and thrilling discovery. It would not be definitive proof of life, as there are non-biological processes that can produce these gases. But it would be an incredibly compelling piece of evidence, a strong indication that the planet's chemistry is being driven by something more than just geology and sunlight. However, the search for biosignatures is fraught with complexities. The atmospheres of exoplanets are vast, chaotic systems influenced by a multitude of factors, including the planet's geological activity, its history of impacts, and the intense radiation environment of its star. Deciphering the subtle signals hidden in the starlight requires immense patience, meticulous observation, and a deep understanding of planetary chemistry. As we stare into the deep, dark spaces between the stars, we are quietly listening for the chemical breath of another world. We are sifting through the faint, filtered light of alien suns, hoping to find the distinct signature of an atmosphere that is out of balance, an atmosphere that whispers of biological activity. We are searching for a sky that mirrors our own, a sky filled with the building blocks of life. But even as we search for these chemical fingerprints, we must also consider the physical landscape of the planet itself. We must descend from the alien sky and imagine what it might be like to stand on the surface of an Earth 2.0. We must look for the scars of a dynamic, restless world. Imagine stepping out of a spacecraft onto the surface of a newly discovered planet. The gravity pulls at you, familiar and grounding. The air, though perhaps slightly different in composition, is thick enough to carry the sound of the wind. Above you, an alien sun shines down, casting unfamiliar shadows across the landscape. If this world is truly a candidate for Earth 2.0, what would you see? Would you find a static, unchanging sphere of solid rock, or a dynamic, evolving world, constantly reshaping itself through slow, powerful forces? Our own Earth is not a static object. It is a restless, shifting planet, driven by the immense heat trapped deep within its core. This internal heat is the engine that drives geology, the slow, majestic processes that build mountains, carve valleys, and shape the continents. The surface of our world is divided into massive tectonic plates, giant slabs of rock that slowly drift across the semi-molten mantle beneath them. Where these plates collide, they push the land upward, forming towering mountain ranges like the Himalayas. Where they pull apart, they create deep oceanic trenches and allow molten rock to well up, forming new crust. This continuous cycle of creation and destruction, known as plate tectonics, is a defining characteristic of our home world. It is a process that operates on a timescale of millions of years, far too slow for us to perceive in our daily lives, but its profound effects are visible everywhere we look. Plate tectonics is not merely a geological curiosity, it is a vital mechanism for maintaining the long-term stability and habitability of our planet. One of the most important functions of plate tectonics is its role in regulating the Earth's climate through the carbon silicate cycle. Over millions of years, volcanoes, driven by the movement of tectonic plates, release carbon dioxide into the atmosphere. This carbon dioxide acts as a greenhouse gas, trapping heat and warming the planet. However, as the planet warms, rainfall increases. The rain washes carbon dioxide out of the atmosphere, dissolving it in water to form a weak acid. This acid slowly weathers the rocks on the surface, releasing minerals that are washed into the oceans. There, marine organisms use these minerals and the dissolved carbon to build their shells. When these organisms die, their shells sink to the ocean floor, locking the carbon away in deep layers of sediment. Eventually, tectonic forces pull these sediments deep into the Earth's mantle, where the immense heat and pressure melt the rock, releasing the carbon back into magma, ready to be erupted by volcanoes once again. This slow, magnificent cycle acts as a planetary thermostat, keeping the Earth's temperature relatively stable over billions of years. Without plate tectonics, this cycle would break down. The carbon dioxide would either build up in the atmosphere, leading to a runaway greenhouse effect, or it would be completely drawn down, plunging the planet into a deep, frozen state. Therefore, when we search for an Earth 2.0, we are quietly hoping to find a world that is geologically alive. We are hoping to find a planet with continents that drift, mountains that rise, and volcanoes that breathe. But how can we tell if a distant exoplanet has plate tectonics? We cannot see the slow drift of continents from trillions of miles away. We cannot directly observe the deep trenches or the soaring mountain ranges. Instead, we must look for indirect clues. We must look for signs of a dynamic, active surface. One potential indicator is the presence of volcanoes. While we cannot see individual volcanoes on an exoplanet, we might be able to detect the massive plumes of ash and gas they erupt into the atmosphere. A sudden temporary increase in sulfur dioxide or other volcanic gases could be a strong signal of geological activity. However, even this is incredibly difficult, as volcanic eruptions are sporadic and often unpredictable. Another more subtle clue might lie in the planet's topography, its overall shape, and the variation in its surface elevation. While we cannot resolve the details of the landscape, we might be able to infer the presence of significant topographical variations by observing the way the planet reflects light. A planet with high mountains and deep valleys will reflect light differently as it rotates than a planet that is perfectly smooth and featureless. By carefully analyzing the variations in brightness as the planet turns, astronomers might be able to construct a rough map of its surface, searching for the broad, sweeping features that suggest a dynamic geology. The search for an Earth 2W is a process of assembling a profound and complex puzzle. We have found the rocky spheres, we have measured their orbits within the gentle warmth of the habitable zone, and we are beginning to peer into their atmospheres, searching for the delicate chemical balance of life. But to complete the picture, we must find a world that is not just a stage, but an active participant in the story of life. We must find a world that shifts and breathes, a world that continually renews its surface and regulates its climate. We are looking for a planet that is as restless and vibrant as our own. As we continue to observe these distant worlds, we are slowly building a deeper understanding of the incredible diversity and complexity of the universe. We are learning that the conditions required for life are intricate and fragile, a delicate balance of physical and chemical forces operating on a truly cosmic scale. The journey to find the closest thing to Earth, 2.0, is a journey of patience, precision, and an enduring sense of wonder. It is a slow, methodical search for a quiet reflection in the dark, a search for a world that, against all odds, has managed to strike the perfect balance, a world that is ready to be called a home. But even if we find a planet that meets all these stringent criteria, a rocky world in the habitable zone, with a thick atmosphere and an active geology, there is one final profound element we must consider. It is the element of time. Time is the invisible architect of the universe. When we look at a planet, or a star, or even a sprawling galaxy, we are not looking at a static object. We are looking at a single, fleeting frame in a cosmic film that has been rolling for billions of years. To understand the true potential of any world, we must understand the sheer, unfathomable depth of the time it has experienced. We often think of habitability as a place, a specific location in space, a certain distance from a star. But habitability is not just a place, it is an era. It is a long, quiet stretch of time where conditions remain stable enough for the delicate chemistry of life to experiment, to fail, to try again, and eventually to take hold. When a planetary system is first born, it is a chaotic and restless environment. A young star is surrounded by a swirling, turbulent disk of dust and gas. Over millions of years, this dust slowly clumps together, forming pebbles, then boulders, and eventually the building blocks of planets. These early worlds are constantly colliding, merging, and breaking apart. It is a period of intense heat and kinetic energy. Even if a planet happens to form at the perfect distance from its star, its early years are too volatile to support anything fragile. The surface is a sea of molten rock. The atmosphere is a thick, choking cloud of volcanic gas, and the skies are filled with the constant rain of falling debris. For a planet to become a sanctuary, it must first survive its own violent birth. It must have the time to cool down. It must have the time for the molten rock to harden into a solid crust. It must have the time for the heavy bombardment of asteroids and comets to slowly fade away as the solar system clears its orbit. This process of settling cannot be rushed. It requires hundreds of millions, sometimes billions of years of patient, steady cooling. On our own world, this period of cooling and settling took an immense amount of time. It was a slow, quiet waiting period in the dark. Eventually, the surface cooled enough for the water vapor in the atmosphere to condense. It began to rain. And it rained for millions of years, a continuous, heavy downpour that slowly filled the lowlands, the craters, and the vast basins of the Earth, creating the first global oceans. This was the beginning of our habitable era. But even then, the Earth was not yet a home. It was just a quiet, wet stone drifting through space. It took billions of more years for the slow, methodical processes of chemistry to weave the first simple threads of life in those deep, dark waters. Therefore, when we look out into the galaxy in search of the closest thing to Earth 2.0, we must look for an old world. We must look for a planet that has been given the gift of uninterrupted time. This brings us back to the gentle red dwarf stars. Earlier, we considered how their faint light and close habitable zones make them prime candidates for hosting Earth-sized planets. But red dwarfs possess another characteristic that makes them profoundly important in the search for a second home. They are the longest-lived stars in the universe. Our own Sun, a yellow dwarf, has a total lifespan of roughly 10 billion years. It is currently about halfway through its life. In another 5 billion years or so, it will begin to exhaust its fuel, expanding and heating up, eventually ending the habitable era of our solar system. 10 billion years is an incredibly long time, more than enough time for life to arise and flourish. But compared to a red dwarf, it is only a brief flicker. Because red dwarfs are so small and burn their nuclear fuel so slowly, they can live for trillions of years. The universe itself is currently estimated to be roughly 14 billion years old. This means that not a single red dwarf in the entire cosmos has ever died of old age. They are the eternal embers of the galaxy. If our candidate for Earth 2.0 is orbiting a red dwarf, and if it has managed to settle into a stable orbit, clear its skies, and hold on to its atmosphere, it will be bathed in the gentle, unchanging light of its star for unimaginably long epochs of time. Imagine a world where the sun does not significantly change its brightness for 1 trillion years. It is a world of supreme, quiet stability. On such a world, the slow engines of geology and chemistry would have an eternity to operate. The tectonic plates could slowly drift, merging into supercontinents and breaking apart again, dozens or hundreds of times, regulating the climate in a slow, rhythmic planetary breath. The oceans would have eons to gently mix their minerals. If life were to begin in those waters, it would not be a rushed, frantic struggle against a changing star. It would be a slow, patient blooming. Imagine the surface of this ancient, quiet world. The mountains might be worn smooth by billions of years of gentle wind and rain. The river valleys would be incredibly deep, carved by the slow, persistent flow of water across hundreds of eons. If the planet is tidally locked, the eternal twilight zone would be a landscape of deep, enduring permanence. The shadows cast by the red sun would never move. The temperature would remain perfectly constant, day after day, year after year, for billions of years. In this environment of supreme stability, evolution could take paths we can barely begin to comprehend. Without the sudden, dramatic shifts in climate that have periodically wiped out large portions of life on Earth, the biosphere of this ancient world might grow incredibly deep, complex, and interconnected. The forests, if they exist, might be ancient beyond reckoning, their roots slowly grinding the bedrock into soil over millions of generations. The creatures that move through the eternal twilight might be perfectly, seamlessly adapted to the quiet red light and the unending breeze. When we look for Earth 2.0, we are not just looking for a mirror of our present moment, we are looking for a world that has been given the time to mature. We are searching for a planetary elder, a world that has sat quietly in the dark, bathed in the soft glow of a steady star, slowly perfecting the art of existence. The search for this world requires us to expand our own perception of time, to step outside the brief, frantic pace of our human lives, and to appreciate the slow, majestic turning of the cosmic clock. We must learn to look at a point of light in the sky and understand that we are seeing not just a star, but a deep, ongoing history. We are seeing a place where time flows like a slow, dark river, carrying the potential of a world from the chaotic dust of its birth into the quiet, stable maturity of a habitable home. As we draw our journey to a close, we must take a moment to reflect on the meaning of this search. The quest to find the closest thing to Earth, ear, is arguably the most profound undertaking in the history of human exploration. We have built towering observatories on the peaks of our highest mountains. We have launched intricate, delicate telescopes into the freezing silence of space. We have spent countless hours analyzing the faintest whispers of starlight, all in the hope of finding a world that resembles our own. But why do we look? Why are we so deeply compelled to find another Earth, out there in the vast, overwhelming dark? Part of the answer lies in our fundamental nature as explorers. Since the dawn of our species, we have always looked toward the horizon, wondering what lies beyond the next hill, across the next ocean, and eventually past the edge of our own sky. The search for exoplanets is the ultimate extension of this innate curiosity. It is the desire to know the shape and the contents of the universe we inhabit. However, there is a deeper, more quiet reason behind our search. It is a reason born of a gentle, collective longing. When we look up at the night sky, for all its immense beauty, it can sometimes feel incredibly empty. The distances are so vast, the silence is so deep, that it is easy to feel entirely alone. The Earth can seem like a tiny, fragile lifeboat adrift in an endless, indifferent ocean. We search for Earth too. Knock, because we are looking for a companion in the dark. We are looking for reassurance that the miraculous sequence of events that led to our existence is not a solitary anomaly, but a beautiful, repeating pattern woven into the fabric of the cosmos. We want to know that the universe is capable of growing gardens, not just in our own small corner, but across the sprawling, spiraling arms of the galaxy. Finding a world with a temperate climate, a protective atmosphere, liquid oceans, and the quiet, steady passage of deep time would fundamentally change our understanding of our place in the universe. It would tell us that the conditions for life are not a rare, impossible coincidence. It would suggest that the cosmos is quietly, naturally fertile. But there is a beautiful paradox hidden within this search. The more we look for another Earth, the more we come to realize the absolute, stunning preciousness of the Earth we already have. Every time we discover a new world that is completely inhospitable, a world of crushing pressures, boiling oceans, or freezing endless ice, we are reminded of the delicate, fragile balance that sustains us here. We are reminded of the perfect, unseen mechanisms that keep our atmosphere breathable, our oceans liquid, and our temperatures mild. We realize that the Earth is not merely a rock we happen to stand on. It is a complex, deeply interconnected system. It is a masterpiece of balance, refined over billions of years of slow, patient evolution. The air we breathe, the water we drink, the soil that grows our food, these are not guarantees. They are the fortunate results of a planetary history that unfolded in exactly the right way, at exactly the right distance from exactly the right star. The search for the closest thing to Earth 2.0 is not a search for an escape route. It is not a quest to find a replacement for our home. Even if we were to find a perfect, pristine mirror of our world, drifting in the habitable zone of a nearby star, the distances involved are so incomprehensibly vast that we may never be able to cross them. The journey would take thousands, perhaps millions of years with our current understanding of physics. Instead, the true value of finding Earth 2.0 lies in the perspective it gives us. It serves as a cosmic mirror, reflecting back to us the immense beauty and the profound rarity of our own existence. It teaches us that a habitable world is a treasure of unimaginable worth. When we finally look away from the telescopes, when we bring our focus back from the deep edges of the galaxy and look down at the ground beneath our feet, we see it with new eyes. We see the green of the trees, the blue of the sky, and the gentle fall of the rain not as ordinary everyday occurrences, but as cosmic miracles. We understand that this small, pale blue dot is a sanctuary, a quiet, sheltered harbor in a universe that is mostly cold, empty, and silent. This could be the closest thing to Earth 2.0. We may find a world with the right mass, the right orbit, and the right atmospheric signatures. We may find a planet bathed in the eternal twilight of a red dwarf, or sitting comfortably in the golden warmth of a yellow sun. We may find a place where the rain falls gently onto ancient silent oceans, and if we do, we will celebrate. We will marvel at the creativity and the abundance of the universe. We will know with a quiet, profound certainty that we are not entirely alone in our potential. But as we celebrate that distant alien world, we must also make a quiet promise to the world that currently holds us. We must remember that for all the infinite possibilities of the cosmos, the Earth is our only true home. It is the world that shaped us, the world that breathes with us, and the world that provides everything we need to simply exist. As the night deepens and the stars continue their slow, silent rotation across the sky, let us take comfort in the vastness above us. The universe is a place of endless mystery and quiet, unfolding beauty. There are worlds out there spinning in the dark, waiting to be found. But for now, as we close our eyes and listen to the gentle, rhythmic sounds of our own planet, let us be grateful for the sanctuary we already have. Let us rest in the comforting knowledge that, right now, in this vast and wondrous cosmos, we are exactly where we are meant to be. Yet, even as we find solace in the familiar shores of our own world, the universe continues to offer variations of reality that stretch the boundaries of our imagination. We have spoken of rocky worlds with temperate climates, places where familiar rivers might carve valleys into ancient stone. But nature is rarely constrained by our expectations. As our telescopes peer deeper into the dark, they are uncovering planetary compositions that are both beautiful and profoundly alien. In our search for the closest thing to Earth. 2. 0. We must be prepared to encounter worlds that take the ingredients of our home and amplify them to breathtaking extremes. Consider for a moment the element of water. On Earth, water covers roughly 70% of the surface. It is the defining feature of our pale blue dot, the cradle from which all known life emerged. But our oceans, for all their vastness, are remarkably shallow when compared to the total volume of the planet. They are merely a thin film resting upon a massive sphere of rock and iron. What would happen, we might wonder, if a planet formed with not just a coating of water, but a deep, overwhelming abundance of it? Astronomers have discovered a class of exoplanets that orbit within the gentle warmth of their stars, yet they are slightly larger and heavier than our Earth. We call them super-Earths, and hidden among these massive rocky spheres is a theoretical subset of worlds that stagger the mind, the water worlds. Imagine a planet where there are no continents. There are no islands, no rocky shores, no mountains reaching into the sky. There is only an unbroken global ocean, stretching in every direction, wrapping the entire world in a sphere of liquid. If you were to descend through the atmosphere of such a planet, you would not see the varied patchwork of green and brown that defines our world. You would see nothing but a smooth, dark, endless blue rippling quietly under the light of an alien sun. The weather on a water world would be driven entirely by the unbroken interaction between the atmosphere and the sea. Without land masses to disrupt the flow of air, the winds could circle the globe endlessly, building up massive, slow-moving storm systems. Yet, beneath the surface of those waves, there would be a profound and heavy silence. As you dive deeper into this global ocean, the light from the star above would slowly fade, absorbed by the endless water. The blue would turn to indigo, then to a deep, impenetrable black. And as you sink further into the abyss, the pressure would begin to build. On Earth, the deepest point in our ocean, the Mariana Trench, reaches down about 7 miles. On a true water world, the ocean might be hundreds, perhaps even thousands of miles deep. At these unimaginable depths, the pressure of the water above becomes so immense that it fundamentally changes the nature of the liquid itself. Long before you reach the rocky core of the planet, the water would be compressed into exotic forms of solid ice. This is not the cold, floating ice we find in our winter streams. This is ice forged by sheer gravitational weight, a dense, hot crystal structure that forms a thick shell around the planet's rocky heart. Could a water world be considered an Earth too? Not. It is a question that invites a quiet sense of wonder. These worlds possess the liquid water we deem so essential, and they sit at the right distance from their stars. But without the shallow, sunlit tidal pools where the chemical building blocks of life could concentrate and combine, the story of biology might unfold very differently. A water world is a realm of absolute suspension, a beautiful, liquid void. It is a reminder that while the universe may use the same ingredients found on Earth, the recipes it follows are infinitely diverse. As we leave the endless oceans behind, we are reminded that habitability is a delicate spectrum. A planet needs water, but perhaps not an abyss. It needs rock, but perhaps not a completely dry desert. The perfect balance is elusive, a quiet harmony of elements that must be maintained over billions of years. And as we continue to map the stars, we have begun to notice something extraordinary. Sometimes, This delicate balance is not just found once in a distant star system. Sometimes the universe places these potential havens remarkably close together, creating a neighborhood of worlds huddled together in the dark. When we look up at our own moon, we see a beautiful solitary companion. It is a silent silver sphere that governs our tides and brightens our nights. But imagine looking up into a twilight sky and seeing not just a moon, but another entire planet, passing so close that you could make out the shapes of its clouds and the faint glow of its surface. Imagine a solar system where the habitable zone is not just a lonely corridor for a single world, but a crowded, gentle hearth shared by a family of planets. As our search for Earth 2.0 has expanded, we have discovered systems that challenge our understanding of planetary architecture, orbiting small, cool, red dwarf stars. Astronomers have found compact systems of rocky worlds, packed so tightly together that their entire planetary dance could fit well within the orbit of our own planet, Mercury. Because the host star is so faint and cool, its habitable zone is pulled in extremely close. And in these narrow, temperate bands, gravity weaves a magnificent choreography. In some of these systems, multiple Earth-sized planets orbit within the life-sustaining corridor. To stand on the surface of one of these worlds would be to witness a sky unlike anything humanity has ever seen. The host star, a large, deep red orb, would hang motionless in the sky if the planet were tidally locked. But the true spectacle would be the planetary siblings. Because they orbit so close to one another, neighboring planets would frequently appear in the sky, much larger and brighter than any star or planet in our own night sky. They would drift across the firmament, casting their own soft, reflected light onto the landscape below. You might see a neighboring world transition from a thin, glowing crescent into a full, radiant sphere as it overtakes you in its orbit. You might watch the shadow of one planet briefly fall across the face of another, a gentle cosmic eclipse happening on a regular, rhythmic basis. It would be a constant, visual reminder that you are part of a larger, interconnected system. This physical proximity creates more than just a beautiful view. It creates a profound gravitational relationship known as orbital resonance. As these planets constantly pass each other in the dark, their gravitational fields gently tug at one another. Over millions of years, these gentle pulls force the planets into a synchronized rhythm. For every 3 times the inner planet circles the star, the middle planet might circle exactly twice, and the outer planet exactly once. It is a slow, majestic clockwork, a silent harmony playing out in the vacuum of space. This resonance keeps the planets stable, preventing their orbits from becoming chaotic and ensuring that they don't collide. It is a beautiful mechanism of celestial self-preservation, a way for multiple worlds to share the same narrow band of warmth without destroying one another. The discovery of these compact resonance systems changes the nature of our search. We are no longer just looking for a solitary Earth 2.0, wandering alone in the dark. We are realizing that the universe is capable of producing clusters of potential. If life were to take hold on one of these worlds, the close proximity of its neighbors opens up astonishing possibilities. Meteorite impacts on one planet could occasionally eject rocky debris into space, carrying the microscopic seeds of life with them. Over time, this debris could gently fall onto the neighboring worlds, potentially cross-pollinating the entire system. A cluster of habitable planets could become a shared cradle of biology, a quiet network of living worlds sharing the same red sun. These crowded neighborhoods of the cosmos remind us that the story of a planet is never written in isolation. Even as a world shapes its own atmosphere and carves its own oceans, it is forever bound by the invisible threads of gravity to the bodies around it. It is shaped by the light of its star, the rhythmic tug of its sibling planets, and the slow, steady passage of cosmic time. As we continue to drift through these distant, quiet systems, we gather more pieces of the puzzle. We map the water worlds, we track the resonant dances of compact planetary families, and we slowly build a deeper, more nuanced understanding of what it means to be a habitable world. The universe is incredibly vast, and its capacity for creation is boundless. Out there, in the quiet dark, the closest thing to Earth. 20 is waiting. And with every shadow we measure and every spectrum of light we decode, we take one slow, deliberate step closer to finding it. As we drift further outward from these crowded resonant systems, we must acknowledge the ultimate boundary of our search. We have explored the geometry of shadows, the delicate balance of the habitable zone, the invisible shields of atmosphere, and the slow, rhythmic breathing of a geologically active world. We have imagined global oceans of staggering depth and planetary families sharing the gentle warmth of a single red sun. Yet, for all our discoveries, for all the data pouring in from the cold depths of space, there is a profound physical reality that we must quietly accept. The distances in the universe are not merely large, they are absolute. When a space telescope detects the faint periodic dimming of a star 50 light-years away, it is not seeing the system as it exists today. It is seeing the light that left that star 50 years ago. The light has been traveling through the silent vacuum of space for half a century before finally brushing against the sensitive mirrors of our instruments. If we were to find a perfect candidate for Earth 2.0 tomorrow, a world with blue skies, white clouds, and the unmistakable chemical signature of a thriving biosphere, it would remain forever out of our physical reach. It would be a lighthouse on the furthest possible shore, a place we can observe but never touch. To cross those distances would require technologies and lifespans that belong to a distant, unimaginable future. Even at a fraction of the speed of light, a journey to the nearest star system would take generations. The people who arrived would be the distant descendants of those who left, born in the quiet hum of a generation ship, knowing Earth only as a story, a pale blue myth passed down through the centuries. Therefore, the search for a second home is not a matter of colonization or escape. It is an act of pure, unadulterated observation. It is a quest for context. Understanding this limitation does not diminish the beauty of the search, it elevates it. It transforms astronomy from a map-making exercise into a profound philosophical pursuit. We are not looking for a place to go. We are looking for a reflection of our own existence. We are seeking to understand if the emergence of life is a rare, accidental spark in a cold, sterile void, or if it is a natural, inevitable consequence of a fertile and creative cosmos. To answer this question, the architects of tomorrow are dreaming of instruments that border on the impossible. They are designing telescopes that will not merely look for the shadows of planets, but will look for the light of the planets themselves. Imagine a network of space observatories flying in perfect synchronized formation thousands of miles apart, acting as a single massive lens. By combining their light, they could achieve a level of precision capable of blocking out the blinding glare of a host star entirely, revealing the faint reflected light of the planets orbiting it. With such instruments, we would no longer be guessing at the composition of alien atmospheres by looking through the glare of a star. We would be looking at the worlds directly. We might see the subtle shift in color as seasons change on a distant sphere. We might detect the glint of starlight reflecting off a vast liquid ocean, a specular highlight that confirms the presence of water with absolute certainty. We might even be able to map the rough outlines of alien continents, tracking the slow rotation of land masses under a strange, distant sun. This is the quiet, patient future of astronomy. It is a slow, methodical peeling back of the cosmic dark. And as we refine our vision, as we learn to see further and clearer into the depths of the galaxy, we must prepare ourselves for the profound emotional impact of what we might find. If we find nothing, if we map 100,000 stars and find only barren rocks, toxic skies, and frozen wastes, the silence of the universe will become heavier, more profound. It would mean that the delicate sequence of events that led to the oceans, the forests, and the breathing life of Earth is unimaginably rare. It would place a monumental, almost terrifying responsibility upon us. It would mean that this small, fragile world is the only keeper of the flame, the only place in the vast, spiraling arms of the Milky Way where the universe has grown eyes to see itself and a mind to wonder at its own existence. The isolation would be absolute, but so too would be the imperative to protect, preserve, and cherish the only home we have ever known. But if we look into the dark and find a whisper of life, if we detect the undeniable signature of oxygen and methane wrapped around a distant rocky sphere, everything changes. The universe would instantly shift from a collection of dead matter to a living, breathing entity. The night sky would no longer be a canopy of lonely fires. It would be a meadow of possibilities. Knowing that another biosphere exists, even if we can never reach it, would weave a thread of cosmic companionship through our collective consciousness. It would tell us that we are part of a larger, grander pattern. As we drift back from the edges of the galaxy, returning from the red dwarfs and the water worlds, our perspective is forever altered. We have journeyed through the freezing cold of interstellar space. We have stood in the eternal twilight of tidally locked planets, and we have imagined the heavy silence of global oceans. We have searched the dark for a sanctuary, a place of perfect balance, a world capable of holding onto an atmosphere and nurturing the delicate chemistry of life. And as our gaze returns to our own solar system, as we see the familiar, brilliant marble of Earth suspended in the void, a quiet realization settles over us. We have spent decades searching for the right mass, the right orbit, the perfect mixture of gases, and the long, uninterrupted stretch of deep time. We have defined the ultimate criteria for a habitable world, a place of safety and profound, enduring stability. When we look down at the slow drift of our white clouds over deep blue oceans, when we feel the gentle warmth of our yellow sun and breathe the nitrogen and oxygen that sustains our very thoughts, we understand the true weight of our search. The cosmos is infinitely vast, and its capacity to surprise us is boundless. There may be countless worlds out there, quietly orbiting their stars, shrouded in the mysteries of deep time. But as we continue to listen to the silent spaces between the stars, we are reminded of a beautiful, grounding truth. This delicate, restless, breathing world we stand upon, with its changing seasons, its flowing rivers, and its rich, interconnected web of life, is not just a starting point for our exploration. It is the gold standard of the cosmos. For all our searching in the dark, for all our dreams of distant havens, this incredibly rare, perfectly balanced sphere of rock and water is the masterpiece. As we look out into the infinite quiet of the night, we can rest in the profound and beautiful certainty that, against all the impossible odds of the universe, this could be the closest thing to Earth, to know. Dro.